Hello. Our advanced mechatronics final is the drone weapon system by me, Jerem Ashford, Kundan Pantha, Bartholomew Hansen, Yen Mo Jim, and Michael Best. Our objective was to build and program a drone to find and shoot a target using computer vision. Our goals are to engineer a drone and build it, program all flight controls ourselves, use computer vision to recognize targets, and shoot the target. I just wanted to explain the Ecalc, which we used to help us determine our components that we would use and to make sure that they were compatible with each other and that nothing blew up. After putting in all the different components that we selected, it outputted what our max current would be and voltage, and this helped us to determine the battery that we would need to use. It also gave us our hover flight time, which is at 7.5 minutes for our current build, and our thrust to weight ratio, which is 4:1, which our ideal would be at least 2:1. So the components on the drone are on the top, it has the Raspberry Pi. Underneath is the Arduino Nano. Here we have a voltage converter. We have 2 of those. Next to the Arduino Nano is a gyroscope. Then we also have underneath that a 4-in-1 ESC. And obviously we have our 4 motors and we have 2 batteries underneath. Then we also, on the front here, we have our Raspberry Pi camera and our laser.
We're using a PS4 controller to tell the drone how to move. So we have these 3 face buttons. The square button, it restarts the Arduino board on the drone if something goes wrong. The triangle button starts all the motors, and the circle stops all the motors. We're also using the directional pad, so up increases the speed of the motors, down decreases the speed, and left and right tells the drone to look left or right. The controller is connected to the Raspberry Pi through Bluetooth. We have a Python program running on the Pi that detects which button has been pressed on the controller. And the Pi has to relay that button press to the Arduino. So we have one pin connected from the Raspberry Pi to the Arduino for each of these buttons on the controller. We're using interrupts on the Arduino to detect when one of these when a control signal has been received from the controller. So the problem is we only have one interrupt pin on the Arduino. So what we're doing is we're activating the interrupt pin and one of the other digital pins at the same time. So when the Arduino detects the interrupt, it checks one of the other pins on the Arduino Nano to see if they have also been activated, and that's how the Arduino knows which input signal has been given. Okay, so we are using a PID controller to control each one of these 4 motors individually. So we're sending a PWM signal from the Arduino to the ESC. The length of the signal is between 1000 microseconds and 2000 microseconds. So this is the front of the drone. These are the front 2 motors and these are the back 2 motors. So if I tilt the drone to the right like this, the motors on the right, they need to increase their PWM values so they keep the drone level. So if we come here to the serial monitor, you can see that the PWM values of the right 2 motors are greater than the ones on the left. Now if I turn it to the back like that, Then again, the back two motors should increase their PWM values to keep the drone level. And we can see that here, the motors on the back, they have a higher PWM value than the ones on the front.
For image processing, we're detecting circles. Over here we have a target. So it can detect if it's a circle or not. We have a function that within parameters it decides, hey, there's a bunch of these gradients pointing at a certain center, so that must be a circle. And if we get enough circles in a group, we decide to keep those circles and throw away the rest, and that is what the target is. The biggest circle that we find should be the radius of the target, and the center should be really close. It usually ends up being really close to the center of the target. So after that, we know where the laser is pointing. It's usually in the same few pixels. So if we get it pointing really close to the center here, it decides to fire. Comparing the distance from the laser to the center to the full radius of the circle. Once it leaves half of the radius of the circle, it should stop firing. But while it's still in the center, it still goes. About right there, it quits. We'll go across again. Right.
Okay, so this is showing the how the camera is actually seeing the target. And as you can see here, you have quite a far distance between us and the target, and we have a few black circles which have been taking the average of those centers, and that gives us the white dot in the middle there is the average center, and then the white circle on the outside right here is the maximum radius that we obtained. And this red dot right there is where the laser is actually aiming. And then we will go ahead and move this forward. And as the drone moves forward, you can see that there are more and more of these circles being detected, until finally at the end we have very many of them being found, and all of them being averaged to create this white center of the target. And for the input that we are giving to the Arduino is over here. We find the circle, this one being the X position of the radius, the Y position of the radius, and the actual radius of the target. Then these next ones are what they say, the distance to the target that it calculated, the angle, and the vertical distance that it would need to move up and down to effectively hit the center of the target. So that's what's fed to the Arduino from the Raspberry Pi for flight control.
So in conclusion, we were able to get all the components to work except for the PID controller. We had issues with calculating the correct gain, and we just ran out of time trying to tune and get the PID controller to work. And thank you for watching.